Hi everyone, today we're going to continue our analysis on this multi-phase problem, and we already discussed part A, B, and C, so today we're going to continue with part D. So in part D, we need to find the net heat transfer input in kilojoule per kilogram. So the net heat is just the heat from 1 to 2 plus the heat from 2 to 3. And we're going to take a look at each of them one at a time. So heat from 1 to 2, if you remember this equation from energy conservation, heat is just the change in internal energy plus the work from 1 to 2, okay? And the internal energy is U2 minus U1 in this case, and then plus work from 1 to 2. We already calculate work from 1 to 2 in part C, so we don't have to worry about that. However, we do need to find the values for internal energy at state 2 and state 1. So if you don't remember how to do that, that's not a problem, because we're going to do that now together. So if you look at this TV diagram here, at state 1, we already discussed this earlier in previous videos. At state 1, it's a superheated vapor. That's where we started. So that's at state 1. So if we want to find anything, any information, any property values about state 1, we need to go to the superheated vapor table. So, and in order to find the right table, we need to know the pressure. So at state 1, we know pressure is 1 megapascal. So we're going to find the table that has 1 megapascal on it. So that is table D dot 3I. So if you go to that table and find temperature, T1 is equal to 680 Kelvin, then we'll be able to find the internal energy for state 1 is 2969.2 kilojoule per kilogram, right? So very similarly, we're going to do the same thing for state 2. But instead of looking at superheated vapor table, we're going to go back to our saturation table, because if you look at state 2, it's right on the vapor dome, so that's when it's a saturated vapor. Okay, so if we go to table D.2 again and find P equals to 1 megapascal, and in this case U2 is also equal to UG, and that is 2582.7 kilojoule per kilogram. So now we can plug these two values back into our equation here, and also the value for work from 1 to 2, and then we get 1632.82 kilojoule per kilogram for heat from 1 to 2. And I'm going to highlight the table that I used to find these values, so it'll be easier for you to look at later. Now we know the heat from state 1 to 2, but we also want to know what's the heat transfer from 2 to 3. So it's very similar. So it's also the change in internal energy plus the work from 2 to 3. So I don't know if you still remember this, but from process 2 to 3, the volume is constant. What does that mean? That means the work from 2 to 3 is 0, because work from 2 to 3 is equal to the integral of pressure times dV. Since the change in volume is 0, so the entire term is just 0. So we can just cross out this term. And then we're just left with delta U in this case, which is just U3 minus U2. We already found U2 in the previous step, so we don't have to worry about that, but we do need to find U3. And it's a little bit different in this case because if you look at our TV diagram, state 3 is inside of the vapor dome, so we actually need the quality to figure out where exactly this state is at. So for state 3, we can calculate the quality using the equation V3 minus V at VF and VS minus VF. So the reason why we chose volume is because we know the volume at state 2 and the volume at state 2 and state 3, they're the same. So let's start listing all the information that we know about state 3. So of course we know all the information should be inside of the vapor dome at T equals to 425K. Okay, so if we go to, and also before we even go to any tables, we know that the volume at state 3, V3, is equal to V2, and it's also equal to VG, because on our TV diagram, state 2 is on the vapor dome and it's super saturated vapor. So if we go to table D.2 again, we can find VG is just 0.19436 meter cubed per kilogram. So I'm going to write that's from table D.2 again. And VF is 0.0010926 and VS is 0.37463, and they're all meter cubed per kilogram, meter cubed per kilogram. So you can find these two values also from table D.2. However, please be very, very careful. This time you're looking at temperature at T equals to 425. Okay. Oh, my bad. Since we're actually looking at temperature, it's actually going to be table D.1. D.1 here. And if we plug in all the numbers, then we should be able to get a quality of 0.577. And if we continue to use table D.1 at T equals to 425, we can find the internal energy at state 3 using the quality that we just calculated. It's 1 minus x3 times the quality when it's a saturated vapor. When it's a saturated fluid or saturated liquid, and then plus x3 times the internal energy when it's a saturated vapor. So if we plug in all the numbers, we should be getting, so let me just put all the numbers in so it's more straightforward. So UF is 639.62 plus x3 is 0.577 times US, which is 2,560.7. So if we do all the math, we should get 1,632.82 kilojoule per kilogram. So that's the internal energy at state 3. So now we can plug all these numbers back into this equation, and then we'll get negative 949.88 kilojoule per kilogram for the heat from 2 to 3. And the net heat, then it's just the value of these two together. Okay, so if we do the math, then I think I made a math error earlier here. So this value is actually negative 502.02 kilojoule per kilogram. Sorry about that, guys. So if you plug that number and this number all together, you will get negative 1451.9 kilojoule per kilogram. And this is the final answer for part D. Yay! I know this is a very long example and you need to look at many different tables, but it's also fun, finding all the things that you need. So I'm going to highlight all these tables so it's easier for you to look at, and also some key equations here, how you use the equation for quality, and how you can use quality later to find the properties that you want. So that's the end of this part D. So let me know if you have any questions. Next time we're going to talk about part E. Thanks.